In this lecture, we will look into an interesting application of the membrane analogy that we have studied in the last lecture. So, let us consider, so what we are going to do is to study the torsion of a rectangular cross section shaft. The condition is that the rectangle, the cross section is a narrow rectangle. Okay. That is a criteria here, and we will get to see why that criteria is there. So, let us consider the rectangular cross section of the shaft. So, this is the x axis. This is the y axis. The dimensions are, this is T, this is B. And B is much more greater than the thickness T. Okay. So, this is the cross section. Do not confuse that this is the shaft, this is just the cross section of the shaft and not the shaft. Okay. Now, if I have a cross section of this form, then you can visualize or you can figure out what would be the deformed shape of the analogous membrane that is going to be of the same shape as that of a narrow rectangular cross section. Okay. Let me reiterate. Now, if this is the cross section of the shaft, then you can very well visualize what would be the deformed shape or deflected shape of the analogous membrane. Okay. Now, let me try to draw the deflected shape. So, the deflected shape in YZ plane is going to be of this form. Okay. So, this is the deformed shape of the analogous membrane. In the YZ plane. So, this is the YZ plane. Okay. And let me also draw the deformation in the XZ plane, so that you have a better visualization. So, in the YZ plane, the deformation is going to look something like this. Okay. So, this is going to be the deformation in XZ plane. Okay. Now, if the shaft, if the cross section is narrow enough, so that B is much more larger than the thickness T, the deformed shape of the membrane in the YZ plane can be very well approximated in this form. Okay. So, this is the approximated deformed shape, approximated or assumed deformed shape in YZ plane. Okay. So, let me again reiterate. So, this red color one is the actual deformation of the analogous membrane, okay, and the black color one is the assumed or approximate deformation of the membrane in the YZ plane. Okay. So, for this approximated deformed shape, the stress function can very well can be thought that the stress function phi is independent of y. For the approximated deformed shape. Okay. So, therefore, from the criteria that we have, which is del 2 phi by del x square plus del 2 phi by del y square is equal to minus 2 g into theta. Okay. We can say that this is going to be 0 because phi is independent of y. So, we are left with del 2 phi by del x square is equal to minus 2 g theta. Okay. So, this is coming from the approximated deformed shape of the analogous membrane. So, now if this is the criteria on the shape stress function, then phi x is going to be, or phi as such is going to be the stress function phi is going to be, I have to integrate this. So, if I integrate this, I am going to get this as g theta x square plus c 1 x plus c 2, where c 1 and c 2 are integration constants. Okay, fine. So, now our next job is to find out c 1 and c 2. Let us try to do so. So, I have phi x is equal to minus g theta x square plus c 1 x plus c 2 x. Okay. Now, let us apply the boundary condition. At x is equal to plus minus t by 2. So, at x equal to plus minus t by 2, from the deformed shape we know that phi is going to be 0. Okay. So, let us find out, impose this boundary condition into this equation and let us see how it is going to work out. So, then 0 is going to be equal to minus g theta t square by 4 plus c 1 t by 2 plus c 2, that is equation A, and then again 0 is equal to minus g theta t square by 4 plus this is going to be minus c 1 t by 2 plus c 2. Let me call this as B. Now, from this two expression, we are going to get C 1 is equal to 0 and we are going to get C 2 is equal to minus g theta, C 2 is going to be plus g theta t square by 4. Okay. Therefore, my stress function phi is going to become minus g theta x square minus t square by 4. So, this is going to be the stress function of a shaft with narrow rectangular cross section. So, this is Prandtl's stress function. of a shaft with narrow rectangular cross section. Right. So, we have done some approximation to get this stress function. The approximation that we have done is the approximation that has been done on the deformed shape of the analogous membrane, and you have seen that the approximation that we have done is very small, right, and it's therefore is a very good approximation of the deformed shape of the analogous membrane. Therefore, the shape function that we derive from this deformation is also going to be a very good approximation of the actual stress function, and therefore, we hope that the following analysis that we do using this stress function is going to be more or less accurate, or it is going to be a very good approximation of the real solution or the exact solution. Okay. So, now if this is the stress function, let us try to find out the shear stresses that are going to occur in the cross section. So, let us see what is tau y z. Tau y z is, so we are trying to find out the shear stress. So, tau y z is minus del phi by del x, and tau x z is going to be del phi by del y. But this is anyhow equal to 0. The tau x z is equal to 0 because phi is not a function of y. So, this goes to 0. So, this we have to not care about. So, let us find out what is tau y z. Tau y z is minus, so minus del x of minus g theta and that is going to be g theta into 2x. Okay. So, therefore, this is the expression for the shear stress 2 g theta x, and only shear stress that is there is tau y z, and tau x z is equal to 0. So, if we try to draw the shear stress distribution, the shear stress distribution is going to be of this form. Okay. So, this is tau y z. This is how it is distributed. Now, let us try to find out the maximum value of the shear stress, right. So, this is the shear stress distribution that we get. So, this is going to be the shear stress distribution when a shaft with a narrow rectangular cross section is going to experience torque. Now, let us try to find out the maximum value of shear stress. Now, we know from membrane analogy that the maximum shear stress on a cross section is going to be at a point where the analogous membrane is going to have the maximum slope of deformation. Okay. Now, for let us just try to visualize the deformed shape of the analogous membrane for this rectangular cross section. Then we will be able to realize that the maximum slope of deformation is going to happen at the two edges, that is at x equal to t by 2 and at x equal to minus t by 2. Therefore, the maximum shear stress tau max is going to happen at this two boundary. So, tau max So, therefore, if I have a shaft with narrow rectangular cross section, the maximum value of the shear stress is going to be 2 g theta. Okay. Now, let us try to find out the torsional rigidity of the rod. We have also understood from the membrane analogy that the torque is the torque that acts on the shaft causing a rate of twist of theta is analogous to twice the volume enclosed by the analogous membrane because of the deformation in the z direction. So, therefore, I can write mt is equal to 2 phi dx dy, okay, and that is going to be minus two g theta. This is going to be minus t by 2, 2 t by 2 and minus b by 2, 2 b by 2 into x square minus if we evaluate this integral, we are going to get mt as if we evaluate this integral, the mt is going to be g theta b t cube by 3. Therefore, the torsional rigidity G j is G b right. So, again this could be this is an approximation of the ideal or exact solution, but again for a narrow enough cross section this is a very good approximation. It is said that if b by t ratio is more than 10, then is equal to 10, then the error that you get, the maximum error that you get is only 6%. So, as b by t increases, the ratio of b by t increases or the cross section gets narrower and narrower, then we see that the error gets on decreasing and we get a very good approximation of the actual torsional rigidity of a rectangular cross section shaft. Now, the obvious question is that why did we spend so much time on understanding the torsion analysis of a narrow rectangular shaft? Because you will slowly realize that this narrow rectangular shaft is the fundamental component of a thin wall structure. Okay. So, almost all thin wall structure are made of this narrow rectangular shaft is similar to a narrow rectangular shaft. So, often this question arises, when are we going to tell that a structure is a thin structure. So, the answer is that the structure is called a thin structure when the ratio of the dimension with the thickness is at least greater than 10. Only then we call the structure to be a thin wall structure. Now, let us see, let us try to extend what we have studied in extend what we have studied and see how physically it varies from the actual or exact solution and what implication does it have on the approximated solution. So, now let me draw the cross section again. Okay. So, with the approximated stress function, we have seen that the only stress that is going to act in the cross section is tau y z, and tau x z is going to be 0. The red colored arrow shows the distribution of tau y z, which is given as 2 g theta x. Now, using this stress function, this approximated stress function, we get the torque is equal to g theta b t cube by 3. Now, there is another way, there is an alternate way by which we can find out the expression of mt in terms of g theta, and that way is to find out the resultant torsional moment produced by the shear stress distribution. So, we have to understand that the moment applied torque or applied torsional moment is being resisted by the shear stress tau y z. Therefore, the moment produced by tau y z is going to be equal to mt. So, let us now try to find out the torque produced by So, if we try to find out the torque produced by the approximated shear stress distribution, let us call that as mt dash. So, mt dash is going to be 2 g theta x, which is tau y z, into b into dx, acting over a small elemental area which is b into dx, into the moment which is x. okay, and the integral of this from minus t by 2 to t by 2. Okay. If we evaluate this integral, we will get this as 2 g b theta minus t by 2 to t by 2 x square dx. If I evaluate that x square dx, so that is going to be 2 by 3 g b theta x cube from minus t by 2 to t by 2. If I evaluate this further, this is going to be 2/3 g b theta t cube into 2 by 8. Okay. Therefore, m t dash is going to be 1 by 6 g b theta t cube. Now, we can see that this is nothing but half of m t. Okay. Now, m t is a good approximation. M t is a good approximation, because it is coming from the deformed shape of the analogous membrane, and which is just a small approximation of the actual deformed shape. So, m t is a good approximation. So, there must be something wrong with m t dash. Physically, m t dash should also be correct, okay, because that is what I am having from the shear stress distribution. So, that should also be correct. So, what is going wrong? What are we missing? What we are missing is the shear stress tau y z, which is going to happen at this edges. We are missing this tau y z. This because of the approximation of the deformed shape near the edges, we have missed out the tau x z that is non-zero near the stresses, near the edges. Now, this tau x z is acting over a small region near the edges, but though they are acting over a small region, their contribution to the torsional moment or torque is large because of the larger moment arm. Therefore, half of this half is coming from tau y z, the other half is going to come. So, another m t dash is going to come from tau x z, which we have neglected because of the approximation that we have done. Now, I should say that though we have neglected tau x z, it does not affect much in our engineering analysis. One, because we are, by using the stress function, we are getting the nearly accurate result of the shear, nearly accurate result of the torsional rigidity. We are getting the accurate distribution of tau y z, which is the prominent shear stress, and we are also getting the accurate value of the maximum shear stress. We are neglecting a small tau x z near the two other boundaries of the shaft, but though that is worth of neglecting. So, we do not mind neglecting that, but you should keep in mind, you should be aware of what is the real life stress distribution, and therefore, you should know that there is a small tau x z distribution near the edges, which we are neglecting in this methodology of solving the problem. But saying that, if we have a narrow enough cross section, this approximation works very well from an engineer's perspective, and we should be happy with the approximation that we have done. So, with this we are done with the torsion of a bar with narrow rectangular cross section. We will see how this becomes useful in analysis of thin wall structure at the later lectures. So, with that I am going to end this module of the lecture.